Okay, awesome. Then let's get going. Right, so this is the first day of class. We always start with searching and sorting. So randomized algorithms, right? So we will be discussing every class a randomized algorithm of some kind. That's sort of how I plan my schedules. I'm going to give you an algorithm every class. And along the way, you'll learn some probability and stuff, and you're going to get much better. And so that should not be too surprising to all randomized classes probably satisfy these things. Often um, I like to pick algorithms to motivate learning some math so that sometimes the mathematical technique just in isolation is a little dry. You can't develop some intuition, but if you see it in action, it's much more exciting, especially because the algorithms are often very beautiful, very counterintuitive. Like there's something very counterintuitive about randomized algorithms and just this idea that, oh, you can do things you didn't think you can do. I mean, I feel like comes up a lot in randomized, and I just don't really try to cherry pick them out of the history of computer science. There's a sort of a secondary goal or approach in the design of the class. Um, so randomized algorithms, you'll see, actually touches a lot of different things. In fact, like for every subfield of computer science, there's that first paper that introduced randomization to it, and it's some epic, massive paper because randomization is very, very basic. And this was also true in economics. This is true with like, quantum physics. You can interpret this way, right? What Einstein did. So the great thing about this class is that we get to hit on like just the greatest hits of theoretical computer science. And so a second point of this class is to sort of also survey really a lot of interesting different points of theoretical computer science and try to also, get you a really wide acquaintance about different things. Sure, for each of those sub areas, we'll focus on some probably randomized part. But I'm hoping to also survey a lot of different topics in theoretical computer science. We'll be doing, there's some things that won't surprise you. We'll do like hash tables, right? Obviously, that's a randomized algorithm. We'll do randomized sorting today. It's obviously a randomized algorithm. But we'll also do like, oh, I don't know, like dimensionality reduction and big data stuff, right? We'll do learning theory, right? Because that's related to actually geometric random sampling properties and stuff like that. We'll do a lot of approximation algorithms because randomization is a really central way to approximate problems. We will do spectral graph theory because there's some very nice interactions between spectral graph theory and randomization and even eigenvalues. Electrical walks have this randomized interpretation. We will do pseudo randomness and we'll even do complexity theory, some hardcore complexity theory, because you'll actually build up the tools. Like a lot of these topics are hard because the tools are tough, but by the time we build them up, you'll actually be able to just kind of just airdrop into all of these awesome different topics. Now, not everyone is interested in every topic. Maybe some people are working on machine learning, some people are working on complexity or something else. But hopefully each of you will have your day of a one lecture or something that maybe is right up your alley. We'll see. But there is an emphasis to try to also, in terms of content, although there's sort of a more vertical um, plan in terms of gradually building up these probability and randomized skills, in terms of the topics I choose, I try to make it really broad and try to find, surprising connections. It really, this topic and a couple others has really helped me form a unified understanding or a more unified understanding of what's going on in theoretical computer science, which is really what makes it interesting to me. I'm much more interested in how things are connected than really any single topic in isolation. It's not clear that any single topic has priority over the others, but once you put them together and see how they're connected, okay, I think that's very beautiful. Okay, okay. Yeah, so much for that rant. Okay, let's do some real work. Okay. So here would have been the itinerary if we had 80 minutes. So we probably won't do all of this. Also, we're going to go a little faster through some parts that's explained in the email based on what students have requested in the past. So we'll see. But I'll still probably just breeze through to warm up. Some basics of probability, the terminology, the notation, and stuff like that. But I really want to focus on the algorithms, and because that's more exciting. That'll get your imagination going, and always the idea is like, oh, if I can get you just little bit excited, then maybe 90% chance you'll look at the notes or something and follow up. So I really want to focus on the algorithms and then bringing in and seeing how the tools are used. And then hopefully, even if some of the calculations or the analytical part is brand new to you, we have all semester to practice and get better at it. That's also what the exercises are for. And especially when I'm back in person, if you really feel a little overwhelmed, but you're still interested, we can come up with a plan and stuff like that. That's quite common. So in this class, I've often seen a very wide range of background, technical, because, we're bringing in a little bit more math than usual, and that can really vary, and that's totally normal. Some of those who maybe didn't do as much probability in a prior class may actually get more out of the class. So it kind of balances out. Okay, so some background on probability, but then really three algorithms I want to introduce because that's the fun part. One has to do with 3SAT. I think you may have seen it before. Another has to do with quicksort, that's sorting. And I will introduce a problem called quick select, but then I'm going to try to leave it to you to analyze it because it's sort of similar to some of the techniques we do for the other two. But it's fun to actually, try something yourself. Okay. But I'll still try to motivate. So it's more fun. All right. So, okay, we'll start with 3SAT. Okay, so just warm up your brains. But in 3SAT, I give you a Boolean formula in what's called conjunctive normal form. So I have this formula phi or phi or something of n Boolean variables, x1 through xn. Okay, and we have this sort of a rigid structure where I have these clauses, okay, which is like, oh, either x1 is true or x2 is false or x3 is true. And if one of those things are true, then okay, that clause is happy, it's satisfied. And so I have all these clauses, and then I have this and, this conjunction in between. And really the original problem is I give you this formula. Can you find some variables to make all the clauses true so the overall formula outputs true, right? And today we're just going to focus on 3 variables per clause, although in general it could be broader. And this is sort of like the quintessential NP complete problem, right? Like this problem comes up 100 million times. Because what is it really saying, right? So at some level, it's saying, here's some Boolean formula. It's really a set of logical requirements. Is there some way to make the inputs satisfy the requirements? And if you can do that, and you can, for example, write down how to cure cancer as a Boolean formula, right? Oh, okay, then that's great. So at some level, anything you can, is sort of a slight hyperbole, but anything you can really ask precisely in the sense of Boolean, right, can sort of be put into this form. And if we had an algorithm to do this efficiently, then we can sort of answer anything that's sufficiently precise efficiently. That would be tremendous, but we don't know, right? We've all roughly tried. What we do know is that from that, maybe it's not so surprising from when it's framed that way, but there's all these other problems that we get exposed to, like independent set or traveling salesman or whatever, that also have this feeling like, oh, that seems simple. That doesn't seem so bad. And they also have this unique property of like, oh, I can actually double check a solution. If the question is there an independent set of size 100 or something, I can actually check to see if, given there's a certificate, right? You could give me an independent set of size K for whatever that requirement K, and I can just double check it's the independent set and that there's K of them very quickly. So any problem that has a certificate like this, you can actually take your algorithm that double checks a certificate. That's a computer algorithm. It runs in polynomial time. And if you do a little bit of hand waving, I mean, you could be much more precise, then you can actually write a Boolean formula that sort of captures that proving algorithm, right? The proving algorithm now expresses a formula that says, oh, if you give me a certificate, it'll answer true if it's valid and false if not. So at some level, any of these problems where you can double check a solution can in principle be solved by SAT. Okay. And then maybe the more clever part is the other direction, is that you can take something very general like SAT and show that, oh, with some cleverness, you can actually create an instance of independent set that will solve your SAT problem, right? So somehow we've come to this amazing stalemate, this draw which at least when I was an undergrad, I didn't even know there was like room for ideas like this idea that things can actually be kind of tied. Okay, so that's conceptually interesting, but you already knew this, hopefully. Okay, so we're probably not going to solve SAT exactly today or anytime soon, but we do want to do the best we can. So one direction is say, oh, I have a formula just like this, and all these things I want to satisfy. Let me instead try to satisfy as many of them as possible. So this is called max 3-sat. Um, right? Oh, sorry, overzealously erasing there. So the goal is to satisfy the maximum number of clauses as possible, right? And this is interesting, even if the formula itself is unsatisfiable, right? It's quite normal. Now you're just in some situation where you're expressing like these things are worth points, right? And you're just trying to get as many points as possible. You're trying to make the world a better place, and you want to make it as much better as possible. Okay. So uh so what the key point, right? Well, okay. So um now if you can solve the maximization problem exactly, then you could also solve the original satisfaction problem exactly, right? Because satisfy as many as possible, and you check to see if you can satisfy all of them. So satisfying as many as possible is also NP hard. The implications are too great to expect a good algorithm. So instead, we do these approximation algorithms, and there's more than a heuristic. Okay, it's formal. We can do things that say like there exists some optimal amount, right? We don't know what the optimal amount is, but there exists some optimal amount. And can you make me an algorithm that guarantees to get at least 50% of optimum, right? Or a solution that gets at least 75% of optimum and prove that it does, right? We'll analyze it and say, no matter what, I'll get at least 75%. That's a reasonable way to approach the situation of, oh, you can't be perfect, right? So how can we try to distinguish one algorithm from another? Oh, I can look at this kind of worst case bound relative to opt, right? So that's the starting point of approximation algorithms. We'll do a lot of approximation algorithms in this class because this is sort of like the next step, maturity wise. How do we live in this post T may not be equal to NP world? This is one way to navigate it. Okay. Right. Now, the great thing is that approximating approximating 3-sat is not necessarily NP hard. Okay. So if you had an algorithm that can guarantee, oh, I can satisfy at least half of the optimum number of clauses, that doesn't tell you if they can all be satisfied. It doesn't tell you what opt really is. Maybe your algorithm gets lucky and gets 66% or something instead. 50% is just a worst case bound, right? So there's just enough gap there where you can try to approximate these problems without trying to solve P equals NP. Okay, and that's important. So, okay, so let's say that the goal is to approximate SAT. So I give you some 3-sat formula, and you want to come up with some strategy to satisfy as many clauses as possible. Okay, so I left a nice blank space to let you guys first look at each other and wonder if you should volunteer, but ultimately suggest some ideas.
You just
Yeah.
randomly assign values.
Sorry?
Can you just randomly assign values to each of the variables?
Okay, so okay, that's one. I can try to randomly assign values. Okay, seems a little silly. I can try to randomly assign values. Okay, and there's another question, right? Like, there's a lot baked into the word randomly. What are maybe and I'll get to Jeanette in a moment. What are a couple ways uniformly at random? So that means x1 is true or false, x2 is true or false. So that's definitely an approach. Okay. But there was at least one other suggestion. Any other suggestion?
Well, I had a question actually. So when
Yeah.
we say that we're approximating like anything between 0 and 1 of the optimal, is it always the same percentage? So if it's satisfying, is it doing the same 50% of clauses that it's able to satisfy, or is there a
Yeah.
difference there?
No, it's a good. Okay, I should clarify this, and I think the general notion of approximation will take a little time to get used to. So it's a good point of clarification. So my goal is for alpha to be as big as possible, right? The more I'm getting relative to opt, the better. So what we're going to do is we're going to come up with an algorithm and prove that it always gets, well, there'll be some randomization involved, but in general, it gets some alpha fraction of opt and we can prove it. Just like we used to analyze running time, say, oh, in the worst case, it'll take this much time. The algorithm might finish faster, but no matter what, it'll take this much time. The algorithms could potentially outperform this worst case approximation factor, but for us, we'll design the algorithm and try to analyze and get the best alpha possible. In fact, one thing generic that's going to happen a lot in this class is that at least I teach the also standard algorithms class. Compared to standard algorithms, there will be some like simultaneous algorithm and kind of designing algorithm, but also a little bit more quantitative thinking in conjunction. So here in approximation, I'm designing algorithms, but I'm also trying to maximize this metric. So you're going to kind of be using two parts of your brain at once. One is sort of this more creative algorithm design, and the other is a little bit of kind of math and maximizing or optimizing this or that. And so that is something that should be new if you haven't done something like this before, and that we'll get some practice with. There will also be other measures of quantitative stuff coming in, because in general, randomization or probability theory is much more quantitative than what comes up in the standard algorithms class. Okay, but continuing on. Okay, so one option was to randomly assign values. Anyone else?
Uh, Pick a random clause and satisfy that clause and then repeat.
Oh, okay. Pick a random clause. Okay, and then make sure I satisfy this one. Well, if I probe further, what are some, I mean, just fun ideas for trying to satisfy?
Just if any of the variables you haven't assigned a value yet, just pick one at random and assign it the value that satisfies the clause.
Okay, pick one at random. So I think you guys have decided that whatever algorithm description, you're going to throw in the word random because that has a higher chance of success than the randomized. Okay. Okay, so that's another. So we have one for each variable, assign a random thing. Another one that seems to be a little bit more careful, right? Because it kind of looks a little bit more at the structure of the formula is to pick a random clause and then maybe randomly try to satisfy that, right? Or sorry, pick a first clause or pick a clause that's yet to be satisfied and then try to satisfy it randomly. Any other fun? Okay, you're all too clever, but usually somebody says, all right, let's look at X1 and let's look at all the clauses containing X1 and see if X1 is true or X1 is false would be better, right? That would be like a very natural greedy algorithm. And then move on to X2, X3, X4. Okay. So that's also, but at some level, this seems like a better algorithm, right? Because at least it's looking at the formula. Like our first suggestion to randomly assign values x1 equal true, x1 equal false has absolutely nothing to do with the input, right? It's an absurd suggestion. Okay. All right. That said, we are in fact going to look at what I call the silliest algorithm. So this is just going to spell out what you already suggested. We'll go through the variables one by one. So there was n variables. So for I equals 1 to n. And for each variable xi independently, I'm going to randomly set it to be true with probability 1/2 and false with probability 1/2. Okay, so that's the whole algorithm, which is what, 2 lines, and even that might be long because you guys just said, oh, randomly set them uniformly at random. That's even a shorter description. Okay, so that is the algorithm. So we're going to do two things. in this class. We're going to prove that this silly algorithm gets you a 7/8 approximation. Okay. And that'll be our first example of approximation. So we'll kind of learn a little bit about that as well. And then one thing kind of cool. So this is a very random algorithm, right? I mean, how could you be more random? We're going to make it into a deterministic algorithm to guarantee that you always get 7/8. And that part's kind of cool. And if you haven't seen it before, that might be more surprising. Okay. Now, later on in this class, we will touch upon, we won't be able to prove in full because that's a PhD thesis. This amazing fact. Okay. There's something called the PCP theorem. PCP stands for probabilistically checkable proof. It states that 7/8 obtained by this absurd algorithm that doesn't even look at the input is the best you can do. For any epsilon greater than 0, if you got 7/8 plus 0.000001, you have shown that P is equal to NP. Okay? That is an amazing fact. I mean, how do you prove that something is hard to approximate beyond a certain point? Right? That's called the probabilistically checkable proof. Right? It has, for example, some connections to error correcting codes and stuff. Because if you think about it, what it's saying is that if you can get more than 7/8 of the clauses correct, you can ultimately solve any formula. And the high level connection to error correcting codes, what error correcting codes do is you're sending messages over the wire, and because wires are faulty, some of the bits get flipped. And what error correcting codes try to do is they try to fix some of the bits and try to recover the original message. And what error correcting codes are started saying is like, oh, well, if you can make sure that 7/8 of the bits don't get flipped, or you can flip up to 1/8 of the bits, and I could still recover the original message. Just sort of in spirit, like saying, okay, if you get, most of clauses, more than 7/8 of the clauses correct, you can recover all of them. That's so okay, there's obvious gaps, but there's a reason why there's some related top techniques between these two things. So error correction is sort of an interesting aspect of randomized algorithms that we'll also touch upon. Okay, so the goal is to prove parts of the PCP theorem, and I think actually more or less establish some smaller constant, like, I don't know, 1/4 or something. Or maybe, maybe we can prove that getting more than 99% of clauses is NP hard, this kind of thing, which isn't as strong as 7/8, but just the fact that we can show anything is pretty big conceptual step. Okay. Okay. So that was our first algorithm I want to introduce. So my idea was to introduce the algorithms first and then come back to the analysis once I've gotten you mildly excited in principle about the algorithms. So, okay, the next algorithm is going to be quicksort. All right, so sorting, as you all know, I'm going to give you n comparable elements. You can think of them as numbers. And I want to sort them in increasing order. As you know, you can do something called merge sort. It's usually lecture 1 in n log n time. And you may or may not know, I do it in my class, is that n log n is actually the best you can do. And you can prove a lower bound. It's not too hard, since I do it in the first day of class, to show that n log n, you actually cannot do better in what's called the comparison model. Okay, so if all you can do is compare two numbers, then actually you need n log n comparisons to guarantee that you're correct. In weird situations, like if the numbers are encoded in bits, there's only a few bits, you can do other tricks. But in the comparison model, n log n is a lower bound. And our quicksort's also going to be comparison based, so you're not going to do better. Okay, and the algorithm is very appealing because it's almost intuitive. Right? It's sort of like a randomized divide and conquer algorithm. So it's based on this idea of pivots. It's a recursive algorithm. And so divide and conquer, at some level, you want to divide the input in half and then work on each half, put them back together. But in sorting, you don't actually know how to divide them in half because they're not sorted yet, right? And that's sort of the chicken and egg situation. Okay, so it's almost like okay, so what's the solution? Okay, you don't know how to get the right pivot. You want to split it in the middle, but you don't know how because you haven't sorted it yet, right? Okay, so you do the next best thing. Okay, well, actually, maybe I can ask you if you haven't seen the algorithm before. How might you go about this? At some level, you want to try to split the input in half, but yeah, you don't want to, of course, sort the input because that's the whole goal. It's like a lazy. Maybe you've all seen it before, so you're too shy to say it out loud. How can I split the input in half without knowing much about the input? That's sort of an interesting conceptual question.
You randomly split until a single comparison needs to be made.
Okay, so what we're going to do is we're going to pick a random pivot. We're just going to pick one of the numbers at random, right? So it might not be in the middle, of course, right? There's a good chance it's going to be in the middle half. Half the time it'll be in the middle half, which is not bad. Okay. But in general, we'll just pick one randomly because we don't really have a better approach. You could actually do, yeah, linear time selection, but that's actually terrible. You would never want to do that. Okay. All right. So you're going to randomly split this thing in half and you're going to look at this number and compare everything to this number and say, oh, what's smaller and what's bigger, right? So I shouldn't say randomly split. You're going to just randomly partition it. And that's going to divide your array into two parts, right? If you're lucky, it's going to be very close to the middle like this, but it could definitely be much more uneven than drawn there. So all you know is you have a pile of numbers that are smaller and a pile of numbers that are bigger. How are you going to deal with these parts?
You recurse on them.
Perfect. We're going to be lazy. We're just going to recurse. Implicitly under the hood, that's going to pick another random pivot and stuff like this, but we don't think of it that way because we are computer scientists. And so I'm just going to sort each half magically by recursion. And then it's easy to put it back together, right? Here's the smaller numbers, put in the middle one, and there's the bigger numbers already sorted, right? I think it's actually much simpler than merge sort because merge sort, you have to at least do the merging and then, you've all written the loops over and over again. And then, oh, you finish one side first. It sucks. Okay. So great. So that's the algorithm. I also think it's pretty silly. You just randomly partition it and you recursively sort both sides. Yeah. It's called quicksort. And actually, for example, Unix actually used this for its sort algorithm. I'm not 100% sure what's actually used, but there's been at times this has been the preferred algorithm. Now they sometimes include heuristics to check to see if the input's already sorted and stuff. All right, good. We will prove two things, not today, in all likelihood due to time constraints. We're going to prove it has a certain running time on average. It's not hard to see that if you get really unlucky with your choices, it can actually take n squared time. But instead, we're going to focus on showing that it has a certain running time on average, independent of the input. So it's sort of like worst case in a certain qualified sense. And then we will, almost certainly not today, show that it'll take this time with exceedingly high probability. Okay, and we'll also formalize what it means with high probability. But basically, you're going to get struck by lightning 1 million times before it looks like the running time doesn't look like n log n. Okay, so it was really, especially as n gets very big. Okay, so in fact, it's more than just average, it's very strongly and highly likely. Okay. So those are, okay, one more algorithm. This is to set you up for the homework. Okay, it's quick select. So the selection problem is very, very similar in the sense that I give you n items that are not sorted. Okay, and the goal is to choose the rank k item. So rank k means like the k smallest item. So a special case would be the median. Find me the median, the rank n/2 item out of this set. Okay. The obvious approach is to sort the number first and then just look up the kth, but that takes n log n. And then there's this amazing median of medians algorithm. It's like a gazillion Turing Award winners that actually takes big O of n time. And although we use it as an example in our algorithms class, actually not a very good algorithm. I think actually most times in practice you're better off sorting first and then just picking the case. Um, but anyway, but it is technically big O of n time. It's very clever. It's a really nice example of divide and conquer. Okay, so quick select is going to be a simpler way to get linear time, at least on average. Okay, so at some level, kind of like divide and conquer. I don't know if that's really fair to say, right? But yeah. Okay, I don't know how to turn this into a rhetorical question, so I'll just give it away. But the first step is just like last time. The first step is we're going to pick a random pivot, right? So it's just going to be some number. Okay, and I don't know where it is. It could be one of the smaller numbers, one of the bigger numbers. So to figure out this number's rank, I'll need to compare it to all the other numbers. So that'll take like n time, right? And then I'll have again the two piles, smaller and bigger. But based on how many numbers are in each pile, I'll either go to the left pile or the right pile. If I'm really lucky, I happen to choose the right element, but that'll never happen. So maybe my rank is bigger than the pivot. So I'm going to recurse on the right side. Okay, something like this, right? And for example, if you know, you're probably going to pick or with 50% chance you'll pick a pivot kind of close to the middle, like in the first half. So you'll throw away half the time 25% of the numbers, right? So that's actually pretty good because if you need linear time each time, if it actually went as we hope, right, it'll take n time, then 3/4 n time, then 3/4 squared n time, and so forth. And since it's geometrically decreasing, it should take n time, right? Now don't take my word should too precisely. I'm going to ask you to kind of flesh that out formally, but you can at least see some of the intuition behind this algorithm. Okay, so that's the algorithm. There's no point in looking at the code. And you're going to prove probably pattern matching off of what we do for quick select, how to get linear time in expectation. Okay. All right. Okay, so those are the three algorithms. And we have five? Oh no. Okay. So we'll do most of the analyses next time. So maybe, bummer. Okay, so maybe what I'll do is, well, let me at least fly through the definitions and stuff, and just to kind of like put it in your brain a little bit, and hopefully it'll wake up some small thing that you tucked away many years ago. And so by next class, you'll be a little bit more comfortable with the terms. Okay, I'll start ranting again. All right, so probability, right? You flip a coin. Is it heads or tails? Of course, you don't know, right? The only right answer is I don't know, right? But you might have also said things like half the time it'll come up heads, right? I've certainly said that colloquially all the time. But what the hell does half the time even mean? There's only one coin, right? If it flips heads, you survive. If it flips tails, Javier Bardem will kill you, right? There's only one coin. So what does it mean to be half the time? Half the time you live? No, you live or you die, right? But I think we all know what we mean. It's like we can kind of imagine doing many experiments of this coin toss. And if I kind of laid them out and looked at it, I expect half and half, right? So there's something kind of intuitive about probability we understand, even though from a certain way it doesn't make sense. It is true that there's only one outcome in real life. So probability is to some extent an exercise of imagination, which is to some extent what math is. Okay. All right, probability theory is going to take events. It's going to assign values between 0 and 1. Each event has also the event where it doesn't happen. Heads, the complementary event, is tails, unless it lands on its side, which usually doesn't happen, at least in thought experiments. Okay. They add up to 1 because one of the events must happen. Something happens or it doesn't. There's some combinatorial stuff you can do. I can say, oh, here's one event, here's another event. I can make an event saying they both happen. That's an event. Yeah, basic stuff. I have two events, right? Some event A happens, and I'm looking at event B. Either B happens or B doesn't happen, right? So here is A and B happening, and here's A and B not happening, and they must add up to A happening, because if A happens, one of those two sub-events happen. Okay? And you can rearrange stuff and you get conditional probability. Okay, so to make things add up to 1, if I divide everything by probability of A, right? That's sort of like, let me zoom in on the universe where A has happened. Okay? And the nice thing is that this becomes 1. So like within the universe, B happening or B not happening adds up to 1. So you have this notion of conditional probabilities, right? Which actually just has this formula. Okay, so if A happens, what's the remaining probability that B happens, right? You have some information and so forth. Okay, in general, whether or not A happens can affect the probability of B happening. Okay, so that's not ever in general true, but if it is true, then we say A and B are independent. That's like flipping two different coins. Hopefully one coin has no relation to the other. You can also say A or B happens, right? That's another event. That's how we can combine events. I know I'm going fast, but I think that's appropriate. You'll get better as we use it in exercises and stuff. There's no reason why it's all going to be super comfortable. One very incredibly useful thing, okay? So in general, if A or B happens, that means A and B happens, or A and not B happens, or just B happens, right? It's the only way to get A or B to happen. Both happen or one or the other. When you start rearranging it, you get something like this, which is very nice. The probability of A plus the probability of B is equal to the probability of the OR plus the probability of the A and B. That actually looks like a Venn diagram if you look at it, right, in terms of areas. And an incredibly useful thing, it's so silly, but it's going to be super useful, is what's called the union bound. If I'm looking at the event of A or B happening, well, A happens or B happens, right? So really this should be, if I basically just subtract this, right? I'm kind of deleting this term, then this becomes a less than equal to, and I get probably A or B happening is less than equal to probably just A happening, not worrying about B, plus probably just B happening, not worrying about A. The reason this is useful, even though it seems weak, is it assumes no structure about anything. You don't have to know anything about A or B to make this work. In the middle of a complicated algorithm, that's super useful. Okay, so my goal is to finish the survey of the random algorithms, kind of terminology, and we'll end there. And then we can analyze those 3 algorithms starting next class. Give me a few more minutes. I blame this on loss in 1106. Okay, taking time to set up. Just kidding. So besides events, there's random variables. So this is when it becomes a little more quantitative. So like when you roll a dice, did that dice come up 1, 2, 3, 4, 5, or 6? And then you can ask questions like, oh, what is the average value and things like this. So when you have these things taking on values, we call that random values, and we'll analyze that as well. The random variable taking a particular value is called an event. You can model coin toss as a random variable. Oh, it's heads or tails, things like this. And then you can ask more complicated things like, oh, here's 2 random variables for 2 different dice. What's the joint distribution? What's probably the first one is 1, the next one is 6, or something like this. These are called joint random variables. So if I can take 2 random variables and kind of look at the tuple, the pair of them simultaneously, that makes another random variable. So random variables can also be combined, and they are still random variables. You can treat them as if they took on one number. And here's this notion of independence. In general, one variable and another may be closely connected. So you can't just break up their probabilities like this in general. But when you can, they're called independent. Okay, we'll see lots of examples. Often an algorithm is very complicated, so you don't have independence. Whereas I feel like when I took introductory probability classes, we often had independence in these contrived examples. But algorithms are complicated, right? One decision affects the rest. One bad pivot may really affect your running time later. So often we don't get this for free, but we'll look out for it. Yeah. Okay. Same coin, different coins. That's an example of independence. Okay. And this will be maybe roughly the last point I want to make. And this is this notion of expected value, which is average. Okay. So often we'll see really demonstrated better next class to map out all the possible outcomes of a random variable is too crazy, right? If I ask for a full distribution of running times, oh, how often does it take n squared? How often does it take n squared minus 1? N squared, that's insane, right? Yeah, it is actually. Thank you. That's insane. But a much more reasonable question is to ask, what is the average running time? So, if you kind of ran this algorithm again and again and again, what do you kind of expect to see, right? And so we'll often be focusing on average because for some reason it just slices through complexity like butter. I mean, for good reason, but for yet unveiled reason. Okay. So the formula is, let me just enumerate all the values it can take on and say, what's the probability of getting this times that value? Probability of this times that value. I mean, we've all used average before, right? Oh, the average midterm grade was 15%. You all know exactly what that means. There's going to be a curve. Okay. So, fine. Here's one really, really important thing. The most important thing to come up this class is something called linearity of expectation. Okay. So if you have two random variables, right, and you're looking at their sum, and these random variables may be completely depending on each other, or they might be independent. You may not know. It may be too complicated to look at, and we'll have examples that will make this point clear in upcoming classes. You want to analyze their average sum. Linearity of expectation says that you can analyze their averages separately and add them up. It's not so hard to prove, and I encourage you to do it as an exercise. Okay? But the average of the sum is the sum of averages. Why is this so useful? It's because there's going to be a lot of messy situations where I can analyze one at a time really cleanly because it's some specific part of the algorithm, right? I'm not worried about how all these specific parts are working together. And a single thing I can analyze by itself, and then I can just add them up. And I lose nothing, right? This is an equality. I can do this piecemeal thing and I lose no information if I'm only worried about the average. That's incredibly powerful. I know you may have seen this before. It might not seem very special, but we'll see all these extreme examples that are like, whoa, I can only make any sense of this with this rule. Okay. And so kind of adopting this and making this something that you fall back on often is one of the biggest maybe tool or things we'll develop in this class. I have there's some conditional expectations. If event A happens, what's the remaining average? You can nest them. Again, not too big a deal. There's some law of iterated expectations. Okay, I won't worry too much about, okay, I'll end here. This will be the last slide, I promise. Usually when I say it's the last slide, it's the second to last slide. And so this is Markov's inequality, which looks fancy, but in fact is. All right, how many students can get 2 times the class average on the midterm? Only half, right? If I told you the average is 40%, only half the class could have gotten at least 80% on the midterm, because otherwise the 1/2 times 80% will already guarantee the average is 40%, right? Almost half the population can be 2 times the average in income or something, right? Same as height, same as anything. This is almost common sense, right? And there's some proof where, you just work it out. It's not too bad. I encourage you to forget this slide and try to do it yourself, because then it'll really, really register how simple this thing is. Okay. This is sort of like linear expectation in the sense that I don't have to assume anything about X except that it's non-negative. Again, you've seen the proof. It's not very complicated. It's not a very strong inequality. It's not very precise in many situations. But because the assumptions are so weak, it actually turns out to be very useful in lots of situations. So this will often happen is that we're interested in algorithms and we want to do complicated things. We don't need to map out some hardcore probabilistic analysis that other fields might do. I'm doing big O notation and stuff anyway. So sometimes having these simpler, cleaner probabilistic tools are more useful because those are the things you can keep in mind when you're designing an algorithm. Okay, I'm already over time, so I'll end there. Next class, we'll just start using these things right away and analyze those fun algorithms that I just went over. I'll probably have to go over them again, but that's okay. All right, thanks, guys, and I'll hang out here to keep answering questions. All right, so last time I introduced a few problems and algorithms, and I thought we'd analyze at least one. But today we'll actually analyze them. So this was the 3-SAT problem, and we're looking at this very simple uniformly random assignment algorithm. And we're going to show not only that this is going to get some kind of approximation ratio, more interestingly, we're going to show how to take this very random algorithm and make it deterministic. We also talked about quicksort. It's funny, I did merge sort earlier today. But quicksort, you pick a random pit, split it in half, recurse, put it back together. We're going to analyze that as well. And right, and I also introduced this quick select problem, which is kind of similar, but for selection, you pick a random pivot, split it accordingly, and recurse on the appropriate part. So, okay. And then we just did like a speed run through basic definitions. What is probability? This kind of thing. And I think at this stage, the more important thing is to start playing with these notions and then just getting better with practice. So, and again, once I'm back in person, if some of these formalities went a little bit too quickly, then we can chat one-on-one and come up with a good strategy. Okay. Linear expectation, that was an important point. I think we also briefly discussed Markov's inequality. The probability of random variable is twice its average, is at most 1/2. Okay, great. Okay, so here we are. Any questions before I start? No. Okay. All right, so 3-SAT, right? So I'm giving you a Boolean formula with 3 variables per clause, and you want to satisfy as many as possible because we don't think we can get an exact algorithm. And actually, you can't even satisfy as many as possible exactly, but we want to try to approximate the best possible quantity. Okay. So we're looking at this silly algorithm where I just flip coins for every random variable independently, comes up heads or tails, and then I assign true or false accordingly. And the claim was that this is going to get you 7/8 of the maximum possible amount, and that's what we're going to analyze first. Okay. So we're going to try some basic cases, just go slowly, especially since it's also our first, randomized analysis together. So I thought the simplest possible thing is just one clause. Okay, so here's some Boolean formula with 3 variables, and the clause is x1 or x2 or not x3. Okay, pretty simple. And so I guess my question is, what is the probability that, or what is the expected number of clauses that I satisfy? There's only one clause, so the expected number is just the probability of satisfying this clause, right? So
3/8.
what is the, yeah,
7/8.
okay, 7/8, but why?
Because each variable has probability 1/2 of being correct, and then the only way that this clause is not satisfied is that all 3 of them are not correct. All 3, x1, x2, and then x3 bar are not correct.
Yeah, so it's actually it's easier to directly see the probability that it's not satisfied. So the only way the first clause is not satisfied is if x1 is false, x2 is false, and x3 is true. Now the coins are flipping independently, so that's 1/2 times 1/2 times 1/2. So that's 1/8. Okay. So the probability that C1 is satisfied would be 1 minus 1/8, and that's 7/8, because it's going to be satisfied or not, so they have to add up to 1. Okay. And then if you really want to do it, the expected number satisfied, well, you sum over all the values, but basically 7/8 of the time you get 1 clause. And I guess the remaining 1/8 of the time you get 0 clauses. So if you really want to draw out the calculation, you conclude, okay, I expect to get 7/8 of the clauses. Right? Okay, good. One clause, not so bad. All right. How about two disjoint clauses? So this is two clauses and they don't share any variables. Right? So
It's 7
what is
8
it?
squared. Oh,
7/8 squared. Okay, so why did you say 7/8 squared?
sorry. That is the probability that both C1 and C2 are true, not the expectation. I'll have to
Oh,
calculate
okay.
expectation.
So let me write out maybe just slowly the expected value definition because I think your observation will help. So technically it'll be 0 times the probability that 0 of them are satisfied plus 1 times the probability that 1 of them are satisfied plus 2 times the probability that 2 are satisfied. Right? So I think the suggestion was that this is 7/8 squared, which is 49, hopefully, over 64. Right? That's 7/8 squared. Okay, good. So that I feel pretty good about. We can try to address the remaining ones. Well, how about this one? What is the probability that none of them are satisfied? One over 64 because
Independence.
yeah. So this is one over 64, which is 1/8 squared. And yeah, maybe the key word here is that they're independent. So the outcome of one really doesn't affect the other. And so your natural logic of analyzing them separately actually holds true in this case. Or more directly, x1 has to be false and x2 has to be false and x3 has to be true. And all 6 have some fixed value. So you'll get 1 over 2 to the 6, and that's actually the same. Okay? All right. What about this probability? What's the probability that exactly 1 is satisfied? 1 over 32. Why?
So first being satisfied and second not being satisfied is it's 7 over 32. So first being satisfied is 7 by 8 and the other not being is 1 over 8 and that happens twice because for two clauses.
Times 2. 7 over 32. Okay, so in one case, the first is satisfied with probably 7/8 and the second is not with probably 1/8, and then the 2 comes from flipping the cases. There's another trick way to do this. Well, I know all the probabilities have to add up to 1, so I don't know if this is any easier, but 1 minus 1 over 64 minus, I guess, 2 times 49 over 60, that's not right. 49 over 64, no, that's also a mistake. Minus 49 over 64. Well, that should give us 7 over 32, I guess. Okay, fine. So we get 7 over 32. All right, so what's 7 over 32 plus 2 times 49 over 64?
It should be 2 times 7 over 8.
Right. So slowly, 7 over 32 plus 49 over 32. I get 56 over 32. And I
7
guess
over
these
4.
things equal 7 over 4. Okay, good. Done. Right? All right, so we got 7 over 4 is the expected number. Great. Okay. It was a little more complicated, but now let's try. What happens if there's one variable in common? This is pretty simple. This is like about as simple as I can make it while not making it totally trivial, right? So just one little notch up, and I put one variable in common, right? So if we did something similar like before, the expected number that are satisfied is going to be 0 times number that's satisfied plus, the probability that 0 of them are satisfied plus 1 times the probability that 1 is satisfied plus 2 times the probability that 2 of them are satisfied. Okay.
I
Which
think
of these?
actually we can write this expectation as the sum of the indicators that either
Yeah,
one of them is
that's the
satisfied.
punchline.
Yeah.
Work with
I
me a
use the
little bit just so
linear.
I can make a point. Okay, so if you try to do it this way, right? Okay, at least probably 0 satisfied, that should be like 1 over 2 to the 5 because there's really 5 variables that have to all be wrong to get 0 of them satisfied. If you want to even calculate the probability that they're both satisfied, it gets a little bit complicated. So on one hand, if this is true, if x3 is true, then they're both satisfied. That happens half of the time. So that would be 1/2 plus, or if this is false, which happens 1/2 at a time, then I'm left with kind of 2 independent clauses of 2 random variables or something. And you want them both to succeed. So one of them fails with probability 1/4. So it succeeds with probability 3/4, 1 minus 1/4, and you need both of them to succeed. Something like this. Right? Okay, but it's already like a little bit more complicated than before. And likewise, we can try to analyze this sort of depending on if x3 is true, if x3 is false. Like we can do it. Oh no, it's only if x3 is false, right? So then it's going to be like, so x3 is false half of the time, and then you want 1 to be true and 1 not to be true, so you'll get like 1 minus 1/4 times 1/4, and there's 2 possibilities because one of them is right and the other one is not. If you really went through this, you'll get 3/4 times 1/4 because the 2's cancel out. That's like 3 over 16 plus, I guess, 1/2 plus 1/2 times 3/4 squared. So 9 over 32. I'm not any better at this kind of math than you are. So what does that get us? Oh, and this has to be multiplied by 2 because you get 2 points for this. You get like 3 over 16 plus 8 over 16 plus 9 over 16. So I get 1720 over 16, which is equal to 5/4. Did I do that right?
You should also times 2 for this 1 over 2.
Okay. This should be times 2. Okay, good. Good. You know it better than me, so you're learning. Okay, good. Right. So I do all these things. 12 plus 16. So we get 28. Well, this is not the most efficient way to do it, of course. We get 7 over a fourth. And after all that mess, do note that it is the same quantity we got last time. Okay. All right. This is a bit of a ridiculous exercise, but you can only imagine how complicated it would be if we had tried 3 clauses with common variables, right? This is just 3 clauses. This is like not that interesting. You could have run brute force on this and actually gotten the true value, right? But the calculations get messier, let alone M clauses, right? If you want to do M clauses, then it's just game over. So, okay. So So again, this is already suggested, so it's not really as dramatic as it usually is. But there is a sort of general question, right, that will come up again and again. How do I analyze some kind of randomized mechanism that has a combinatorial explosion of possibilities, right? So these overlapping clauses rapidly made our calculations much more complicated, and trying to map out all the outcomes was like tough enough with two clauses and one variable in common. I actually made a mistake along the way, right? So that's the general setup that we'll often find ourselves in. This is just a warm-up example. So the real big idea, right? The real big idea is that I'm only asking for the average. I'm not asking to map out necessarily all of these possible outcomes. Oh, what are the odds of getting the first clause, but not the second clause, and the third clause? We don't necessarily have to do that. We just have to output the average, right? That's just like one number. That's much smaller than mapping out all cases, right? So you might think, okay, if it's a smaller thing, then maybe there's a more. So we'll do something which, if you haven't seen before, might be counterintuitive. We're going to model this as random variables for every clause. Okay, so I'm going to set up this variable yi for clause I. Okay, and it's just going to be 1 or 0 to say whether or not the clause is satisfied. So it'll be 1 if the ith clause is satisfied, and it'll be 0 otherwise. Okay, that's not so interesting. It's just a Boolean indicator. Okay, so the sum of yi's is what we're really after. Okay, so the sum over all the clauses of yi, this is, by definition of our random variable, the expected number of satisfied clauses. I mean, just how we modeled things. Okay. Now, let's just look at one of these in isolation. Right? What's the expected value that the 10th clause is satisfied? Oh, that's just the one clause case that we had no problem with. Right? So what was the answer? What is the expected value of yi for
7/4.
7/4. 7/8.
Yeah,
Yeah,
sorry.
7/8. Yeah, we can't satisfy more than one clause, of course. And okay, so 7/8. And keep in mind, that was a relatively simple calculation. Right? Okay. So now let's look at this thing we really want. Right? The expected number of clauses that are satisfied. Again, that's going to be the sum of the random variables. Right? Okay. At this level, we haven't done anything, right? When it's all inside here, we're still complicated. All the yi's are related to each other, right? This is one term that captures all of the weird ways they might be related. Okay. So now how do I make progress? What's the next step?
Switch the summation and expectation.
Yeah. So this is the great part. The expected sum is equal to the sum of expectations, right? This is so powerful. Because once I put it in this terminology, or this expression, right? I've actually completely separated the clauses. We no longer worry at all about one clause depending on another, right? It's a small change in notation. Not much ink was spilled, but conceptually, you've taken some potentially super nasty, super complicated, we can't solve these formulas, right? It's NP hard, right? We don't have better than brute force. We don't have strategies to pull apart formulas, right? But linear expectation just slices through this and separates it for you. Right? I know it seems simple, but it's quite profound. Or so I claim. Okay. And now you know what each of these are, right? This was 7/8. So you just multiply it by m. And you say, I'll satisfy 7/8 of the clauses in expectation. Very simple, right? but it's completely put away. It just completely dismisses all the potential complexity of the formula. Okay. Good. Okay, so we know how to do 7/8. Now the other thing I promised, we're going to take this insanely random algorithm. I couldn't make a more random algorithm. And I'm going to make it not random at all. That's pretty cool. Okay. So, right. Okay. Well, maybe I should first open the floor. Can anyone, especially if you don't know the answer, try to, Beckler, anyone want to suggest how to take this algorithm and make it deterministic? Or just ballpark loose ideas? Because it's an interesting question and you deserve a chance to try it. Okay, that's fine. So, all right, what about something relatively elementary like this? Okay, so I'm concerned with this sum, right? And I'm just using z so I don't have to rewrite the sum over and over again. So I know the expected value of z is good when I do this random experiment, right? But we can also pull apart some by conditional expectations, x1 is true half the time, and the other half, it's equal to false. Okay, so this is really the probability that x1 is equal to f. Okay, so I've taken my expected value and I'm conditioning it on the value of x1. Right? Okay, how about that for a hint? It says that the expected value of z is equal to the average over two conditional expectations. The one where x1 is true and the other where x1 is false.
Can you just iterate through I from 1 to n and then compute the expectation condition on x1 and choose the one with the larger expectation?
Yes, that will be. So let me take a baby step to get there, right? So this quantity is good and is the average of two quantities. So one of those two quantities must also be good, right? The maximum of these two conditional expectations, okay? So the maximum is at least the average, which is equal to the original expectation. So some choice is good. There exists a good choice. How do you identify the good choice? Maybe I'll just ask you to say it aloud again, right? So one of these two choices is good. How do I figure out the good choice? How do I calculate it? I want to actually be able to calculate these quantities exactly, and then I can just choose the better one.
You loop through all the clauses and see how many clauses are satisfied with x1 being equal to true.
Okay, so I can like go through all the clauses and add one if ci is satisfied by x1 equal true and 0 otherwise, kind of thing.
That's what I was thinking.
All right, that's quite reasonable, but it's close. But this equality is actually not quite exact.
So you count the ones that contain x1, and then for the ones that does not contain x1 or x1 bar, you just take 7/8 times the number of clauses.
Yeah, so let me Okay, so that's kind of what it is. So if we apply the formula for linear expectation slowly, right, you'll get, you go through all the clauses and you get all of these individual expectations given x1 is equal to true, right? So I can look at each clause and reassess this expectation. So if the clause contains x1, then certainly you just get 1 point. And if it contains x1 bar, you get 0 points automatically, right? Oh, sorry. If it contains x1 bar, what's left is a clause's two variables. I'm glad some of you had your screen
3/4.
on so I could see you. Yes, so you could see,
3/4.
I can see you're disgust. And so those become only 3/4, right? And then there's some clauses that never had x1 and those remain 7/8. So you kind of have three cases, 1 or 3/4 or 7/8, depending on, but it's very easy to write an algorithm to just go through and count the number of variables left, right? And then based on that, you'll add 7/8 or 3/4 to your running total. So you can look through and actually calculate this expected sum exactly, right? So it's not quite this, but this was pretty close. Okay. I've made a mess of things. Okay. All right. So that will help you address the first random variable, right? You can do this and figure out which one you need. So in an induction step, maybe you've already you figured out the first variable, say if k was 1, right? Now you have to figure out the second variable. And how would you do that? I'm getting this like duh bouncing head. So someone just fill it in and put us out of our misery.
You just do the same thing again, but on the formula where you've now substituted in the correct value of x1.
Yeah, so you can always put in another conditional expectation, right? So what am I doing? Okay, so this is just writing out the average that, okay, it's one of these two things. And I already know by induction, this value is good. So one of these two values must be good. Again, how do you determine which one? Oh, okay, we just do the linearity of expectation. This would be a sum over all clauses of the expected value of yi conditional on all of these random variables. So you just go in and plug in and reassess, right? But you actually have out comes a deterministic algorithm from all of this, right? This algorithm that's inspired by complete chaos, right? But the algorithm ultimately never flips a coin. It just recalculates things based on what you would get if you flipped these coins. Right? So that's like very surprising. Does that count as a randomized algorithm? I don't know. Yeah, but I think it fits the class, right? But it's kind of very cool, right? So you get this 7/8 approximation ratio deterministically, after all. Okay. Yeah. I mean, the other remarkable fact is that we don't think you can do better than 7/8. Okay, so that's also the best possible algorithm in the worst case for general 3 set. Okay, good. All right, that's one. Let's knock out another one. We'll do a quick sort.
I had a
Yeah,
small question. How did
absolutely.
you define this goodness thing? Is it like
Okay. So yeah, let me go a little more slowly. So this thing is 7/8m, right? That's what I meant when I said it's good. Because that's what we calculated before. If you had done the random
I mean,
experiment, you get.
if you select the minimum at a certain step, maybe you will get a better results at a future step. Can that?
It might actually get better. That's absolutely true. In the worst case, you're only promised to keep it the same.
Okay.
And then otherwise, you just calculate the thing and choose the better of the two options. Yeah. Okay. Okay, good. Other questions? That was a good question. All right, marching on. Let's do some quicksort. So quicksort was this algorithm that's like a randomized divide and conquer, where we choose a random pivot, split the input accordingly, recurse, and put it all back together, right? I think this algorithm, because of the recursive nature, it's a little bit harder to see what's going on, right? Like, what if I chose, a really bad pivot that actually split the input like this, right? Then I have this very lopsided thing and something's going on later. And how does that, compare to, like, I don't know, getting a bad pivot at the end? So it seems like getting a bad pivot at the beginning is worse than getting a bad pivot at the end because the input's bigger. I don't really know, right? But you can just imagine that, oh, it's this sequence of choices, right? It feels adaptive. That's a little bit different than what we just did, where it was kind of easy to see all the clauses in some static way. So that's maybe why this might seem more involved than last time. Okay, so we're going to try to show that it takes n log n time on average. So, okay, so we'll just do this like we normally do, right? So the first thing to do is to just try to model the running time as an equation, right? So it seems like it's going to be something like t of k minus 1 maybe, plus t of n minus k. So you'll choose some number which will be the kth largest, where k is some uniformly random choice. And then you have to glue them together. So say big O of n. Okay. So, right, I mean, you have to split them apart and glue them back together. So that's some linear time overhead. Okay, so this is the kind of formula we're used to, but k is uniformly at random, right? So if we really mapped out like all the possibilities, we want to calculate. Well, let's see what's written underneath. Oh, okay. So we kind of want to calculate this quantity, expected value of t of n, right? And there's basically all these different choices of k. K is equal to 1 of n, from 1 to n, and each will happen with probably 1 over n, and the expected value will kind of be like the expected value of these subcalls. Something like this. This is quite a bit messy, right? Because, I mean, it looks compact, but this is really a summation of 2n terms. Usually we do recurrences with like 1 or 2 terms, right? So this is quite messy.
There should be a big O then.
Yeah, there should. There should. Okay, good. So, all right, but let's say, just for building some ideas, there's some luck involved, right? Depending on the choice of k. But ideally, what would be a great choice of k?
N over 2.
Or 2.
Yeah, right in the middle, right? If you're able to split this thing right in the middle, then you would get this recurrence that's basically just like merge sort. 2tn over 2 plus big O of n, and you get your n log n, right? What's the worst pivot? 1, if I chose the extremes, I'm not really decreasing the input size at all. So in the worst case, you have this like t of n is equal to tn minus 1 plus t of 1, right? And that's going to lead to n squared because you're going to need n time plus n minus 1 minus n minus 2 plus n minus 3 and so on and so forth. And that's certainly possible. That's well within the realm of possibility. Well is a strong word, but it's definitely in the realm of possibility. So this is sort of the situation we're in. Ideally, the best we can do basically is n log n. The worst we can do is n squared. And it's possible. It's not impossible. And it seems complicated, right? How does the choice of the first pivot affect the choice of future pivots? Right? It seems complicated to think about a dynamic algorithm making random choices. affecting the recursion tree along the way. Okay. But again, we're just interested in the expected running time. Okay, so I'm only worried about the running time on average. It's still worst case in the sense of no matter what input you give me, what is the average running time? So it's a worst case analysis in the real sense of the word, like robustness to different inputs. That's what we're interested in computer science, right? But it's not worst case in the sense of what's the unluckiest possible coin tosses. Okay, because we kind of control that randomness. We don't have to treat that as an adversary. Okay, so I don't know. Does anyone want to, at least if they don't know the answer, speculate on how to go about this? Mostly, yeah.
Can you solve a recursive equation? So
you could actually try to take this and fight through it. But and I've done it, but it will be definitely messy, as you might imagine. Yeah, but that is definitely possible. And maybe if you've done this kind of thing a lot before, you can handle the notational complexity and figure out how to represent it more compactly. So that is possible. It's not impossible. That said, what we're going to do is much more slick in any case. So the running time is really proportional to the number of numbers that get compared to each other, right? In one iteration, I pick a random pivot and I compare it to everyone. And it's like n comparisons. And so if you just add up the total number of comparisons this algorithm makes, that's a pretty good model for the running time. Okay. So we're going to make indicator variables. So it's going to be 1 if the I smallest element is compared to the j smallest, and 0 otherwise. Okay, this is very similar to what we did last time. We're setting up indicator variables. So the sum over all these variables, that's the total number of comparisons by definition. That's basically the running time, right? Up to a constant. Okay. All right. That's really the biggest step. It's just this conceptual leap, right? And maybe I gave you the answer, so it might seem simpler in hindsight, but trying to identify the right indicator variables to unravel the analysis, that's really the point of emphasis. Okay. Good. So the expected sum, that's our average running time up to a constant. And of course, what's the key glorious step? How do I proceed here?
Linearity of expectation, you take the summation out.
We'll use linearity of expectation, right? Look at this. I now have a sum of averages where I'm only worried about 2 numbers, right? I was so worried about like this butterfly effect, bad pivot, good pivot, but somehow that's all unraveled. Okay. So did I leave anything here? So now I just have to analyze each of these terms by itself. Okay. So this is what we're looking at, right? Here's my random variable. The expected value, because it's just a 0, 1, is going to be the same as the probability that they get compared, right? So I sort of have this like array of numbers at the bottom from I to j. Okay. What are the kind of necessary and sufficient conditions? This part's a little tougher. This is more conceptual. Trying to analyze the probability that number I is compared to number j in increasing order.
In the selection process, if I or j are selected before any elements within I and j?
Yeah, so if j gets selected, then it'll get compared to everyone, including I. Same with if I get selected. But if we select something in the middle first as a pivot, then I and j will be split up. They'll never be compared. Okay, so we can expand this out, and this will be the probability that I or j is selected before any element between them. And then what are the odds of this happening? Yeah.
2 over j minus I plus 1.
Yeah, so this will happen with probability 2 over j minus I plus 1. Because any of them are equally likely to get picked first. If in one round of the game, none of them gets picked, then they're going to be on the same side, and you repeat the game. Right? There's no bias introduced. Everyone is treated equally. Okay, awesome. That wasn't that bad of a calculation. You have to see it the right way, but otherwise, as far as numbers being involved, it wasn't so bad. Okay, so we have this thing, we set this up, and we'll just finish off our analysis. So I'm summing from j is equal to I plus 1 to n of 2 over j minus I plus 1. Okay. I find this easier if you rearrange the sum. Okay, so this is again just 2 over j minus I plus 1, because j being the bigger of the two. And this is really 1 over, or 2 over 1, plus 2 over 2, plus 2 over 3, up to basically 2 over j. Right? Okay, maybe I'll put the 2 on the outside. So what is this inner sum, roughly?
Harmonic numbers.
Yeah, it's a harmonic number, so this is about log j. Do you guys know the easy way to see this? So the sum of 1 over I from, say, up to n, that's going to be at most the integral from 1 to n of 1 over I. And this is log I evaluated at n plus 1 minus 1. Okay, so you have this xy curve, and instead of doing the summation, you do the integral. That's all. Okay. Okay, and then, so these are each at most log n. You end up with n log n. Okay, awesome, right? But it was getting the right expected values and things just fall apart. Okay, let's try to do one last thing a little more ambitious. I want to show that it's going to take at most n log n with high probability, and over the course of this, we'll clarify what we mean by with high probability. Okay. So we're going to frame the analysis a little bit differently. For an element E, I'm going to count how many times it appears in a subproblem before it's done. Right? So if there's always good pivots, it'll probably only appear in log n, but it might appear in more depending on how the pivots are chosen. And each time it appears in a subproblem, it gets compared to the pivot, right? So that's another way to try to account for all of the subproblems. Okay. So my claim is that for any particular element E, the odds of it being, say, 32 times log n is really small, like 1 over n cubed, polynomially small in n. Okay. So if that were true, right, what I really want to show then is this quantity, right? If I can show that all the elements appear in at most about log n, right? Then that means there's at most n log n, or 32 n log n. Okay. So suppose this was true. All right, we'll do this afterwards together. But suppose this particular claim was true, that any particular element is going to show up in at most 32 log n with probability of error at most 1 over n cubed. Now I want to show that all of them, right? So how would I do this?
Use the union bound.
Yeah, there's a big hint in the middle. So the probability that sum exceeds this bound is at most the sum of probabilities of any of them exceeding this bound. Okay. And so this is at most the sum over all the elements of 1 over n cubed, if indeed that claim is correct. There's n elements, so you get 1 over n squared, right? So for the larger inputs, which are the ones we're concerned with, this probability plummets to 0 rapidly. That's what we mean by high probability. The error goes down polynomially small in n. Okay. So it's actually very, very reliable as well. You're really not going to see it take more than 32 n log n time for any large input ever. Okay. And this is even a crude analysis. One can do more
I
complicated
had a quick
things.
question.
Yeah.
Why can we apply the union bound? Because we're doing a max here. Where is the and or the or happening?
Good point. Good point. So that's right. So this is sort of like saying DE1 is at least 32 log n, or DE2. Yeah. So the max is just some compact way. The max is bigger only if at least one of them is bigger. So it would really be an or over all the elements.
Okay.
Yeah. And so those are the n events that we're oring over.
So what I find interesting is that we claim that the probability of for all e is less than 1 over n cubed. And then the probability for the max is less than something that's bigger than 1 over n cubed.
Yeah, so any individual one has probability 1 over n cubed. So if I looked at this one element by itself and didn't worry about anything else, that's how I get to 1 over n cubed. Now I'm worried about any of them screwing up.
Okay.
And that's why it gets a little worse. But we just naively add them up with the union bound.
Okay.
Yeah. Okay, good, good. Okay, so all that's left is to prove this claim. And what are we going to do? This will be a little bit more involved. But I'm going to set up this, I'm fixing E for the rest of this analysis. And we're going to say, okay, how many elements are in the subproblem after 5 recursive calls, 6 recursive calls, 7 recursive calls, right? Because it's navigating some branch of the recursive tree. So the first one, x0 is n, right? Because at the beginning it's with everybody, so after 0 recursive calls, everyone's there. And it becomes 0 as soon as E is selected as the pivot. Okay. So, fine. And in general, DE is at least I only if xi is greater than or equal to 1. So if I can show that x of 32 log n is almost definitely less than 1, then that will give us what we need. That's the high level setup. So the next step is to try to upper bound the expectation, especially for large I, like our I being about 32 log n. Okay. All right, so we're going to do an easy analysis. I mean, a crude analysis. So ideally, we want to pick things from the middle, right? So let's just say a pivot is good if it's from the middle half. Otherwise, it's bad, right? Now, if a pivot is good, then from E's point of view, at least some fraction of the elements will split off. What is that fraction?
1/4.
1/4 of them. Okay. I guess if there's k elements left, then k over 4 would be split off. So, okay. So let's, for example, analyze the expected value of x1, right? So x0 is n. So, and we just want a modest upper bound. Okay. So just a less than equal will be fine as long as we make good enough progress. So we can condition it on it being a good pivot or a bad pivot. So half the time, let's say half the time it's a good pivot. In which case the value is at most
K
3
over 4.
over 4.
perfect. 3n over 4. And in half the time it's a bad pivot, in which case it's at most just a weak upper bound is fine.
And
Yeah, n. 7/8 n. Okay. And we can do this for all i's, right? So assume xi minus 1 is fixed, right? So that's sort of treated as a fixed value. And now we can do this conditionally. So half the time you pick a good pivot, in which case you get, oh, okay, we'll hop off soon. 3xi minus 1 over 4. Okay. Plus half the time you get xi minus 1. Okay. We put this together, right? Each one goes down by 7/8. Originally you start at n. The expected value of xi is at most 7/8 I over n. Okay. So, okay, that's easy to do. You just unroll it. I'm going a little quick because somebody's getting bullied. We don't like that. Okay. Now, which I think is also slightly inappropriate, but anyway. We're probably always going to go 5 minutes over. So I guess when I'm there, we'll hold our ground. Okay. But if I plug in k is equal to 32 log n, I get 7/8 to 32 log n, right? And then this, we can write this as 1 minus 1/8 32 log n. Okay. Now, I guess log, natural log, it doesn't matter. Okay. Now, one thing kind of annoying is that I have one quantity down here and one quantity up here. And there's one absurdly useful, absurdly simple inequality that sort of helps us clear this up. Does anyone know it? You might have seen it before, you might not.
1 minus x less than equal to exponential minus x.
Yeah. So this inequality is true. Okay, it's because the exponential curve kind of looks like this and the linear function goes underneath it. You can see it in the Taylor expansion, but it's okay. I think I left it as a homework problem. But this is like one of the most incredibly useful things. It seems crude, but watch how it's useful. So I put the 1/8 in the corner and I get e to the 1/8 times 32 natural log of n, right? And then I get e to the 4 ln of n, and I guess we allocated more, oh, there should be negative. Okay. And so you get 1 over n to the 4th. So I guess n cubed was actually not correct. It should have been n to the 4th before. Okay.
I think you need to multiply by n, right?
At the end. So at this point, we're just focused on the one element case for this claim. And yeah, then you'll get an n back. So I guess I should have either made this 24 or this should have been n to the 4th. But it's not too big a deal. Okay. So the expectation is now 1 over n. Oh, no, I know why. Okay. The expectation is at most 1 over n to the 4th. Right? So now let's look at this. what is the probability that, right, so let's see. Okay, so the probability that you're in more than this many subproblems is the probability that xk is greater than or equal to 1. Right? It has to be at least 1 to get this. Right? And I know the expected value is really low. So it's quite unlikely for this value to be so much larger than the expected value. Now we'll bring in this Markov's inequality. Okay, where alpha is equal to 1. Expected value of x is 1 over n cubed, I guess. It's really 1 over n to the 4th. This square goes around, sorry. So you get 1 over n cubed. Okay, and you're done. That's where this Markov's inequality comes in. The average is so low, you're not likely to be that much larger than the average in a multiplicative sense. And that completes the claim. Okay. So relatively elementary. We didn't do too much crazy math, though maybe more than you're used to, but at least it was like I've had harder calculus tests and stuff. Right. So, but we were able to prove some pretty strong results about quicksort. The real thing is seeing it the right way, setting up the indicator variables the right way and all that stuff. Okay. That's it. Quick select is pretty similar, and so you'll get a chance to try out some of these ideas on another, very common algorithm. And if you really get stuck, it's quite easy to find on the internet, but try not to. So you should be able to kind of pattern match off of what we did here and be able to come to similar nice results for quick select. Okay, and that's all I had. And yeah, it took 2 classes to do 1 class worth, so we'll see how this goes. But that's it for today, and see you in person on Friday.